Hey everybody, this is your first honors calculus video, and this is going to be a review of rational functions. Now, we reviewed several things from pre-calc already. The first one was solving trig equations, and then we reviewed the unit circle, and then we reviewed how to graph sine, cosine waves, and did some problems with those. Now we're going to review rational functions because we're very close to starting limits, and rational functions are the best place to start at limits. If you can't graph a rational function or find asymptotes for it, then you won't be able to find the limits. So this is a great place to start here for our discussion on limits this week. So for the video, make sure you write down everything that's written here. Any visuals, include them. Don't mute the video, don't fast forward, just watch the video, get all the notes down, and the stuff that you have here will help you in class. So first of all, a rational function is any function that can be written in this form right here. F of x equals p of x over q of x. Now, this is a textbook definition right here. Basically, this just means if there's an x in the denominator or in the bottom, then it's going to be rational. Also, you can't divide by 0, which is why we say q of x, whatever's down here, it can't be 0. It's impossible to divide by 0. Now, this definition refers to a polynomial. So just recall, several function types now. Linear functions are lines, quadratics are parabolas, cubics are anything with an x cubed, and it keeps going downwards. A polynomial is any function that goes in decreasing order with the exponents. The exponents are whole numbers. I should add this, they're whole numbers. They go in decreasing order. They can't be decimals or fractions. So there's infinitely many examples of polynomials, but anything like this, where the exponents are getting smaller, that's a typical polynomial right there. And the graphs are just curvy shapes like this. So you've seen these graphs before. This is just summing everything up together. So basically, if you take two polynomials and you divide them, you get a rational function. So if I have this, I have a polynomial here, I have a polynomial here. If I divide them, if this isn't 0, then I have a rational function. That's all there is to it. To find certain parts of rational functions, you're going to need to know what the degree of a polynomial is. The degree of the polynomial is just the highest exponent. So in this case here, this polynomial, the degree would be 4, because the highest exponent is 4. In this case here, the degree would be 3. Here, the degree would be 4. So you just look for the biggest exponent in the whole thing. So pause the video if you need to get any more of this down. And then once you have it written down, unpause it and keep listening. Now, the thing that makes a rational function special is it has asymptotes. Without an asymptote or asymptotes, it wouldn't really look rational. There are 3 kinds of asymptotes: vertical, horizontal, and slant. So you're going to want to make sure you get all this written down here. Vertical asymptotes represent a domain restriction. Remember, domain is x. They just tell you what x cannot be equal to. To find the vertical asymptote, which is something you're going to need to do a lot, you're going to set the denominator equal to 0 and then solve for x. Whatever that x value is, that's your vertical asymptote. And I'll show you examples of each of these. The horizontal asymptote represents end behavior. Now, end behavior is basically what the y values approach as x gets very, very large. And let me clarify. It's as x gets very, very large positively, and as x gets very, very large negatively, in both directions. It shows you where the function levels off. And this idea of leveling off is key when it comes to graphing these and when it comes to limits. To find the horizontal asymptote, you're going to have to remember these 3 cases, which you've seen before and worked with before, but in case you forgot them, I'm going to rewrite them here. I'd like you to write them down as well. You compare the degrees of the numerator and the denominator. If the degree is bigger on the bottom, the horizontal asymptote is 0. An example of that would be 3x squared plus 7x over 4x cubed plus 8x plus 1. The degree on top is 2. The degree on the bottom is 3. The degree on the bottom is obviously bigger than the degree on top, so the horizontal asymptote there would be 0. So when you plot it, you would put a horizontal dotted line right at y equals 0. If the degrees are the same on the top and the bottom, the horizontal asymptote is going to be A over B. A and B are just the, not quotient, it's coefficient. Whoa, sorry, just kidding. It is the quotient of the leading coefficients. So A over B is the quotient of the leading coefficients of the numerator and the denominator. So let's take this one right here. That should be an M. How about ax cubed plus 7x plus 1 over 6x cubed plus 8x plus 2. The degree on top is 3, the degree on bottom is 3. The degrees are the same. So you take your leading coefficients. Y would be 8/6, which is 4/3. So whenever you plot this thing, if that's 1 and that's 2, 4/3 would just be a little bit above 1. And that's your HA. If the degree is bigger on top, there will not be a not be a horizontal asymptote. Instead, there's something called a slant asymptote, which is the third kind of asymptote. Let's do 3x to the fourth plus 7x over 2x squared minus 1. Degree on top is bigger than degree on bottom. So there's not going to be a horizontal asymptote. You have a slant asymptote, which would look something like that, or a dotted line going down. A slant asymptote is always a line. So let's go ahead and start graphing these. To graph a rational function, you need to find and plot the asymptotes. You need to find and plot the x and y intercepts. You have to find and plot additional points. Connect the points using the asymptotes as a guide. So get that jotted down before we do examples. You're going to have to find x and y intercepts to help you connect some dots here. To find the x-intercept, just set the numerator equal to 0, solve for x. To find the y-intercept, you set x equal to 0 and solve for y. That's always true. To always find a y-intercept, you always set x equal to 0. So make sure that's written down, and let's go to our first example. So I'm going to run through these relatively quickly because this is review for you. The degree is 1 on top, 1 on the bottom. It's the same, so I'm going to do the quotient of the leading coefficients. 2 over 1 is 2. The vertical asymptote, I set my denominator equal to 0, and I solve for x. This implies that x is negative 5, because if I plug negative 5 into here, I would get 0 in the denominator. To find the x-intercept, I set the numerator equal to 0. That means 2x equals negative 3, which means x is negative 3/2. Write it as an ordered pair. To find the y-intercept, you let x be 0 and solve. 0, or simplify, I should say. That all cancels. 3/5 is your y-intercept. 0, 3/5. So let's plot everything. I have a horizontal asymptote of y equals 2. I have a vertical asymptote of 1, 2, 3, 4, negative 5. So set up a graphing grid on your paper with tick marks and plot along with me. My x-intercept is negative 1.5, so put that on the x-axis. My y-intercept is 3/5. So on the y-axis, a little bit more than a half. I don't really have enough points to connect. I mean, I know these two are going to connect, but I don't know what's really going on. So you should always pick extra points on each side of your vertical asymptote. I already have 2 points on this side of that vertical asymptote. I don't have anything over here. So how about negative 8 and negative 7? And then I'll just do one more at like 2 to see what this thing is doing. So all you do is plug it in. All right, so I plug my points in, and again, wherever there was x, I plug that in, and I get my y values. So you have negative 8, 5, 6, 7, 8, 13 over 3, at a little bit more than 4. Then at negative 7, you have 11 over 2, which is 1, 2, 3, 4, 5.5. At 2, I'm at 1. So I have 5 points. That's plenty here. And I know that it's going to go between these two. I know that I cannot cross the vertical asymptote. So noticing that as I go from left to right here, I'm going up. So I'm just going to continue it and get close to the vertical asymptote, but don't touch it. Here, as I go left, I notice it was going down, so I'm going to continue it, and it's leveling off at the HA. And I know my work is in the way, but make sure it gets close to the HA. Here, I'm noticing this upward trend. I'm going to continue it, get as close to the HA as you can. It levels off there. Here, it's generally going down. I'm going to continue it going down. It cannot go through the VA, just get close to it. It shoots down. Here you can write some limits, and we're going to actually write them so that you get used to this, but we're going to do it in class. So make sure you have the graph, and then we're going to go ahead and write the limits in class on top of the graph. Let's do one more example here. The HA is going to be y equals, degrees are the same, leading coefficients 1 over 1 is 1. The VA, x squared minus 9 is 0, x squared equals 9. That implies x is 3 or negative 3. Check it out. You have two vertical asymptotes. Here, my x-intercept, I'm going to set my numerator equal to 0. X squared is 4. This implies x is 2 or negative 2. You also have two x-intercepts. Y-intercept, you let x be 0. And I get 4/9. So 0, 4/9. That's a 4. All right, so go ahead and plot everything. I went ahead and I plotted my two x-intercepts, my one y-intercept, and my asymptotes. And I noticed that I don't know anything about the graph here or here, but I do know what's going on right here. It's going up and then down. So I can assume that as I go to the right, I can continue going down, but I cannot cross the vertical asymptote. I can either shoot up or down. And seeing as it's going down to the right, I'm going to continue down. Going left, I can see that it's going down, so I'll continue going down, not touching the VA, getting close. So I really want you to write this down here as reminders. You can cross the horizontal asymptote. You cannot cross a vertical asymptote. The graph either shoots up or down. And when you draw, you get close to the asymptote. The graph is approaching the asymptote all around. So then I saw that I want to try doing negative 6 and negative 4, and then 4 and 6 to see where the graph is. And again, just to demonstrate, you just plug your x values right into the function. 32 over 27 is 1.185. At negative 4, just to save time, I'll just tell you it's 1.714. So fill this table out in your notes. At 4, I have 1.714, and at 6, I have 1.185. So hopefully you notice that symmetry. I have here and here and here and here. Same y values for the x values that are the same but opposite in sign. Whenever there's two vertical asymptotes, there usually is some symmetry. So I'm going to plot 1.1 and 1.7. Again, we're not computers, so we can't plot perfectly these decimals, but just do your best. And I can see, just notice, is it going up or down? From here to here, it's going up. So continue going up, shoot up at the VA. From here to here, it went down, level off. This is key. It's going to continue leveling off forever to the left. Here, it's going down slightly, so continue going, but leveling off at your HA. Here, went slightly up to the left, so shoot up. Whoop. There you go. Now, a couple things to keep in mind here. I want you to write down the following rational function, and it's y equals x squared plus x minus 2 all over x minus 1. So write that underneath this statement here. A rational function can have a hole in the graph if there's a common factor in the numerator and denominator. So I went ahead and I graphed this, or I'm going to graph it on my graph here. And what is this? I have a line. I graphed a rational function. There's an x in the bottom. And I got a line. What is going on here? And if I go to my table, I can see that I actually have an error at 1. There's nothing at 1. If I trace this thing, let's see if it'll do it. As I get close to 1, oh, it jumped over it. But there's an error at 1, so we need to investigate a little bit more closely what's going on here. What you do for this one is if you factor the top and rewrite the bottom, there's a common factor that cancels. So I'm really just left with x plus 2, which is a line. We'll talk more in class. Write all this down. Bye-bye.